Hello everyone, I am Dr. Alok Agrawal, working as an associate professor in the Department of Mechanical Engineering, Sagar Institute of Research and Technology. In this video, we will continue our unit 4, that is fan blower and compressor, and we'll see very important terms related to the power absorbing machine, which deals with the fluid as air as a fluid or gas as a fluid. The topic is static head, total head, and isentropic efficiency. This is very important topic to understand the working of compressor, fan, and blower. So let us first see what is how the static and total head values are determined and what is the difference between the. So when we will deal with reciprocating compressor, there is a reciprocating part in it, and the speed or we can say the velocity of that part is comparatively low. And because of that, the air or gas interact with that compressor, its velocity is also low. So generally we neglect that velocity when we will deal with the energy equations. But in case of centrifugal compressor, the RPM of the rotating element is very high. And so the velocity of air or gas encountered with it is also very high. So it should not be possible neglect that velocity as a lot of energy are associated with that velocity also. So in that case, we need to talk about the total head quantity. Actually, what is this total head quantities? It is the amount of energy which a fluid is having with respect to its enthalpy. And in addition to that, we will consider the kinetic energy of the fluid also. And when these two energy combine together, we get a total head values. Okay, so to understand it in a more better way, let us consider a horizontal passage in which air is flowing, and this passage is of varying cross-sectional area. So let us see, portion one is the inlet and portion two is the outlet. And what we are considering that there is no work interaction between the system and surrounding. This is our system, and there is no heat interaction between the system and surrounding. And when we apply steady flow energy equation between section 1 and section 2, what we will get? We will get internal energy at section 1 plus flow work at section 1, and then the kinetic energy at section 1, and that will be equal to the internal energy of section 2, the flow work of section 2, and the kinetic energy of section 2. So this is showing the law of conservation of energy as no heat and work interaction is taking place between the system and the surrounding. So this U1 plus P1 V1, it can be replaced by the enthalpy at inlet. So let us replace it by the enthalpy part, that is U1 plus P1 V1 is the enthalpy at inlet, and U2 plus P2 V2 is the enthalpy at outlet. We know that this enthalpy can be written as Cp T1 because enthalpy there is thermal energy associated with it, and this is can be expressed in the form of temperature and specific heat of the air or whatever fluid we are talking about. So what we will get Cp T1 in place of H1 and Cp T2 in place of H2. Now we can say that the addition of this enthalpy and the kinetic energy is a constant because at inlet and outlet they both are equal. So we can consider it as a constant quantity and we will give it as equation number 1. Now see in this equation what is happening. This is T is called static temperature. Now see what is static temperature means we are calculating or we are experimentally determining the value of temperature of air, but that temperature is static. And when we call it as a static temperature, when the measuring instrument, that is thermometer, is traveling with same velocity with which the fluid is traveling, means there is no relative motion between the flowing fluid and the measuring instrument. And in that case, when we are getting the temperature, we call it as a static temperature because in that case, the kinetic energy of fluid is not taking into account. So here what is showing T is static temperature because kinetic energy is not included in it. Okay, so we called it as a static temperature. Now, what is stagnation temperature or stagnation properties in which the measuring instrument is stationary and flowing fluid will flow around the measuring instrument and will go. In that case, what is happening? The fluid which is coming in contact with the measuring instrument, its kinetic energy is reducing because when it strike the measuring instrument, its kinetic energy will be zero. In that case, the complete kinetic energy is converted into other form of energy, say temperature. In that case, whatever the measuring instrument gives reading, it is not static temperature, it is a stagnation temperature. So this is the main difference between static temperature and stagnation temperature, or static value and stagnation value. Static values are those values in which the measuring instrument travel with the flowing fluid with same velocity, and there is no relative motion between the measuring instrument and the flowing fluid. But in stagnation, the measuring instrument remain stationary, and in that case, the kinetic energy of the flowing fluid will be taken into account. So now let us move forward. So what is happening? Whatever I have explained, it is written here that if the moving air brought to rest in reversible condition, the total kinetic energy, what will happen, will be converted into the heat energy, and thus increasing the pressure temperature of the air. This temperature and pressure is called stagnation or total head pressure and temperature or stagnation property. So if we'll see that if we consider this is a static part temperature and we consider velocity associated with it, we can get Cp T0, and this T0 is stagnation temperature. Here, this stagnation temperature, the kinetic energy is associated with this. So T0 will always be greater than T, because in T, kinetic energy is not associated, and in T0, kinetic energy is associated. Okay, so if we'll rearrange this equation, what we'll get? We'll get the difference between the stagnation temperature and the static temperature, which is V square by 2Cp. So we are giving equation number accordingly. Now, for finding the total head or stagnation pressure, we can use same expression that we are using for static temperature and pressure. That is P0 by P will be equal to T0 by 2 to the power gamma upon gamma minus 1. This is a thermodynamic relation that everyone knows. So this P and T in this equation, this P and T are static quantities and P0 T0 are stagnation quantities, and it should be kept in mind that stagnation properties can be equal to the static property can be equal to the stagnation property, but it can never be less than static property. Okay, so this is the case for stagnation and static. Now, if we'll see here the graph between T and S, we'll see that whenever there will be a flow of fluid, that is, the state 1 will move to state 2, but there is always a friction between the air molecules and between the air and blade passages. So there will be a more heat generation because we are doing work. That compressor is a power absorbing device, so we are doing work into. So when there will be a transfer of energy, the temperature of air will increase or temperature of gas will increase. But because of this friction between the molecules of air and between the air and the blade passage, the actual rise in temperature will be more than the reversible rise in temperature. So this will give rise to the entropy. Now see what is happening. We cannot say that this process is isentropic process, because during this process the entropy is increasing. Entropy does not remain constant. So to keep the entropy constant, what we need to do? We need to extract the heat from the system at the same rate at which it is generated. So in that case, what is happening? The process can be isentropic, but now we are interacting, the system and surrounding are interacting in terms of heat, so it will not be an adiabatic process. So the process can be adiabatic or it can be isentropic. Okay, so this is the case. Now let us see the what is isentropic efficiency. So it is defined as the ratio of isentropic temperature rise to the actual temperature rise. It can be seen from the graph that what is actual temperature rise or isentropic temperature rise. If we'll consider the entropy constant, and we will start from stagnation temperature, that is T01. It will, if we will consider it isentropic, it will move to T0 or 02, and the corresponding temperature is T02 dash. But what is happening? We have already seen that there will be a more heat generation as compared to the reversible or isentropic process. So in that case, the outlet temperature will be more than the T02 dash temperature. So let us consider it T02, because the process is not isentropic. It will not be a straight line. It will be like this. And if you want to see what is the difference between T02 means the temperature at stagnation point and the temperature at static point, we can see that it is C2 square by 2Cp, which has been seen in equation 2 or equation 3. So what is the isentropic efficiency? It is the isentropic temperature rise, that is T02 dash upon minus T01 divided by T02 by T01. And we can say that this T02 minus T01 will always be greater than T02 dash and T01. So isentropic efficiency or any efficiency should be less than 100%. And if we want to evaluate in terms of static condition, we can write similar thing, that is T2 dash minus T1 upon T2 minus T. So this is about isentropic efficiency. Now see what is happening here. That I have already discussed that compressor is a power absorbing device. Hence, during the process of compression, work has to be done or imparted to the impeller. So we'll talk about the energy balance equation. So how we need to include the work part in it. So this is the initial energy and this is the final energy minus the work done should be there, so that to equate this equation. Now what is this? This combined will give Cp T02, T01, sorry, and this combined will give Cp T02. So it can be replaced in static value can be replaced with stagnation value, and what we can get? We can get that work will be equal to Cp T02 minus T01, and this work input is a product of a specific heat at constant pressure and the difference in temperature. So this is isentropic efficiency that we have discussed. Or then if we'll multiply and divide both numerator and denominator by Cp, we can get this, and this is isentropic work and this is actual work. So isentropic efficiency can also be defined as the ratio of isentropic work to the actual work. So this is all about isentropic efficiency and isentropic. Thank you. Thank you very much.